All right. In this module, we're going to talk about a concept called fracture toughness. And so incorporates what we were talking about with stress concentration and resistance to failure via crack propagation. So to kind of derive this expression, we want basically to get a critical stress for crack propagation. So the stress at which crack propagate in brittle materials. And so the way we do this is by balancing the energy required to form these new surfaces if the brittle material fails and creates two new surfaces, and also the strain energy. So basically, the energy that goes into straining the material. And so we can basically calculate this critical stress by a number of factors. So the elastic modulus E, the surface energy, the length of the interior crack. So this is an expression for the interior crack. So all of this kind of goes into that expression. And so again, this is for brittle materials. For ductile materials, we would actually have another energy for plastic deformation. So this is just for brittle. We'd actually incorporate additional factor for ductile. So the result of that is that, or to kind of go along with that, materials are obviously going to have numerous cracks of different lengths and orientations. So that's kind of just a given, right? We don't have the scenario like this where we have just one or two perfect flaws at the right orientation. In our real materials, we have a number of these cracks, and they can be different lengths and orientations. And so crack propagation and therefore fracture is going to occur when our stress at the crack tip exceeds this critical value that we have for a crack at the lowest critical value. And so, again, that's kind of similar to the resolved shear stress concept because it's going to basically look for the crack that would initiate failure the first, right? So if you have a bunch of defects in a material and you have one really large one at the right orientation, right, that's the one that's going to cause failure, and all those other small ones don't really matter. And so that's kind of the importance. So the largest, most highly stressed cracks grow first, and so if they do so unstably, the other ones don't even matter. And so that's important in these materials. So that brings us to the concept of fracture toughness. So this factors in both stress on the material and the crack length, so a measure of this crack size. And so what the fracture toughness is a measure of a material's resistance to brittle failure when a crack is present, because they are always present. And so basically, this is a very important mechanical property because it's going to tell us whether something will spontaneously or very rapidly fail when brittly fail when a crack is present. And so this kind of factor is very important for things that obviously you want to avoid fracture, which is almost everything, right? And so fracture toughness is Kc, K with a capital K with a subscript C. This has interesting units of megapascals times the square root of meters. And that's equal to y, which is a dimensionless parameter. And then it's multiplied by that critical stress for crack propagation, and then multiplied by the square root of pi times the crack length. And so if you have a planar specimen, like a sheet with a crack much smaller than the width, then that y becomes 1. So this is kind of a geometric factor that's involved in this material. So this is fracture toughness. And there are different types of fracture toughness by different ways that it interacts with the crack. And so looking at crack opening. So in tensile mode, this is known as mode 1. So this is the example here or here where we have an interior crack or surface crack, and we apply tensile stress, and it's basically trying to open this crack and cause it to propagate towards the right. So this opening here. So basically it's like a mouth, right? And it's trying to open up the mouth. That's what mode 1 is. And this is going to be the most common one that you probably see. And it gets, since it's mode 1 or Roman numeral I, we call fracture toughness in that mode K1C or KIC, depending on how you read that. But that the Roman numeral there tells you the mode. And so in this case, it's opening, mode 1, and so that's the modification. There's also other modes, so you can talk about sliding. So this kind of looks like an edge dislocation, shear motion. That's mode 2. And then tearing, which kind of looks like a screw dislocation, that's mode 3. But again, mode 1's the most common. That's the one you're probably going to see the most frequently.